John started his journey with a grant from the National Science Foundation to study solar-assisted heat pumps as an undergraduate at Syracuse University in 1975. Upon graduation in 1977, he went to work at Carrier Corporation, ultimately designing multiple heat pumps, and was awarded the United Technologies Design Achievement Award. To satisfy his entrepreneurial itch, he left Carrier in 1988 to help start up Geotech, a geothermal installation company that was subsequently sold to Atlantic Energy, and in 1991 started Phoenix Energy Supply, a wholesale distributor of Geostar, Samsung, and Net Zero heat pumps. He also started and operates Earth Sensitive Solutions LLC, a design and consulting firm, Source Rock Geothermal, a turnkey loop installing company, as well as GeoGlide LLC, makers of the popular GeoGlide polyethylene fittings. So I'm thrilled to introduce John. Just a little bit of experience there. We're anxious to hear your presentation.
Yeah, I probably could have shortened that for you, Jeff, but I don't get this opportunity very often, so I figured I'd load it up.
It's great to have the experience.
Thank you, Jeff, not only for the introduction, but what IGSFA has done in the last couple of years is phenomenal. And I applaud all the work in these Dig Deeper webinars and town hall meetings and all the other activities you've got going on. So job well done. I looked through the participant list, and yes, I know quite a few of you, but allow me to introduce you to my younger self. Yes, as Jeff mentioned, 75, I was working on heat pumps in the sub-basement of Link Hall. My lab partner was working on gas furnaces, and I wonder what he's doing today. Anyway, the other interesting point of this from this clipping, which I dug out of one of my mother's boxes, the heat pump I was working on was actually built by Singer. So that's a name we don't see in the industry today. So without further ado, let's move back to the question at hand. Why do we put balance valves on loop field manifolds? Frankly, I don't have a clue. I don't understand why engineers want to put balance valves on loop field manifolds. So hopefully diving deep into the technical quantitative look at the use of a balance valve, maybe we can improve how we approach loop field design. As Jeff mentioned, it's my responsibility to point out any conflicts I may have. Well, I do sell balance valves, so that's my conflict. So here I am, and part of me wants to sell more valves. Another part says, well, what's the right thing to do? So there's my conflict. So let's dig deeper. Let's start off by getting us all on the same page with what is a balance valve. We're going to talk about the energy impact and pose the question, is balance important? And I'm going to try to illustrate this with a couple of case studies. So a balance valve is nothing more than what we call a Venturi nozzle, or taking advantage of the Venturi effect, which we can measure a static pressure differential as we accelerate the fluid through a nozzle. And this difference in pressure from the upstream to the restricted area of the nozzle is what gives us the ability to correlate that pressure drop to a flow rate, and then we can dial it in to be whatever flow rate we want. And balance valves serve an extremely useful purpose on devices that we do want to control flow rate as precisely as we can. Most balance valves, plus or minus 5%, is a pretty standard accuracy that they promote. Some of the better ones go as far as 2% accuracy. Here's some pictures of some balance valves. The Belimo, which to me is the premium standard in the industry for all sorts of valves. They're not cheap. This is a 2-inch valve, $432. Jomar makes a great valve. You can find it online for $258. The valve we tend to choose when we sell valves used to be called FDI, and now they're called IMI, Hydronic Engineering. We sell that for about $250. So how does a balance valve actually work? So these nozzles have a pressure drop curve that as flow rate goes up, the pressure drop goes up as well. So let's use an example of a flow of 54.4 GPM. We'll come back to that number later, but we're going to use that as our example. So at 54.4 GPM, the pressure drop is going to be 140 inches of water column. Turns out to be 11.7 feet of head. And at that flow rate and that pressure drop, that's 150 watts of energy needed to create that flow dynamic. And that's just to overcome the pressure drop of the balance valve. So let's pose the question, is balance important? One of my favorite phrases ever is we measure it with a micrometer and then we cut it with a chainsaw. And I'll give credit to the late, great Dr. Jim. I don't know if he came up with the phrase, but it was characteristic of him for sure to have phrases like this. We miss you, Jim. Another dimension that engineers often fall victim to is what I call the delusion of precision. Geothermal loops are not like a Baltimore air coil device. It is not 100% quantifiable and predictable in how it's going to perform. We do the best we can to quantify it and design, but we delude ourselves into thinking that there's something precise about a loop field. I'm going to illustrate this with our first case study. I've got 92 bores in 23 groups. Each group consists of 4 1.25 inch loops down a 490 foot bore. We're running 2-inch out to each of these groups. And the length of that 2-inch supply and return varies from 100 to 400 feet. The system design flow was specified at 1250 GPM. The pump was specified at 85 feet ahead and 50 horsepower. The group flow rate, 1250 divided by 23, 54.4. The loop flow rate turned out to be 13.6 per loop. This is a sort of a plan view of the loop field. Each one of these boxes, either blue or green, illustrate the 4 loops that are part of a group. And the furthest one down here in the lower left takes about 400 feet of pipe to get all the way back into the building. The closest group, only about 100 feet away. And we're talking one-way length. To be precise, you want to look at the elbows and essentially look at the equivalent length. And one thing I wanted to point out, I always measure to the middle of the reverse return manifold, because one leg of that manifold goes to the opposite end and the other end starts at the beginning. So we pick the midpoint and calculate our lengths based on that. We actually designed and provided the manifold on this job. I did speak to the engineer asking if he would allow us not to use balance valves, but he wanted them. So we incorporated into it the balance valves. Here's the picture of the actual installation. It's not very often you get to work outside and install a manifold. And actually use some reserved parking, as these signs behind here are kind of interesting. But obviously they're going to build a shelter around this, and it becomes the manifold room, if you will. So I want to illustrate this by using one of our design tools that we developed to help us quantify loop field performance and flow dynamics. So I'm going to walk you through this. You'll see a lot of slides that look like this, so I want to get you somewhat familiar with what we're doing. First thing, we specify the bore depth. We can use this to model horizontal loops. So if you have a 600-foot horizontal coil, we would put a bore depth of 300 feet. So we have to sort of fool the program a little bit. We specify the size of the loop field and a number of feet per ton. We also specify the flow rate in GPM per ton. We specify the antifreeze that's going to be used. In the upper right, we specify the number of loops in the design, and all these numbers come together to define the flow rate per loop, as well as the total system flow rate. We then walk through and we put in the number of header pairs or number of groups. We've got 23. Minimum operating velocity, we have arrived at a number of 1.5 based on the trade-offs between higher velocity for the sake of motivating air to continue to move through the system. And if you push that velocity up too high, you start to pay a penalty and pressure drop. So we've arrived at designing at 1.5 as a minimum operating velocity. We can then also specify the length between loops. 20 feet is pretty typical. We then enter the length one way to the worst case group. So we're out 400 feet away, and we've got 2-inch pipe headed out to that group. Our program will calculate the maximum pipe size in each section of the reverse return manifold. This keeps these pipe sizes consistent with our goal of 1.5 feet per second velocity. So this sort of sets the boundary. We don't want to go bigger than what the maximum calculated size is. However, we do override what the program suggests or calculates as a maximum, and we can reflect the actual sizes that were called out in the design document. So we can enter those numbers. Over on the left, we can pick any size loop pipe you want from 3/4 inch up to 4-inch. And honestly, I've never seen a 3 or 4-inch loop, so we just put it in the matrix here to have it available. Down at the bottom, that reflects a Green Abilities twister coil, which consists of 4 3/4 inch loops. And then we merely select the specific size we want on a given job. In this job, it was 1.25 inches, and that's being reflected up here. And this number here is what guides us. We feel if we can get the loop pressure drop to be at least 70% of the total pressure drop of the system, that it will just naturally balance. And in this case, it's telling us that this model is telling us the bulk of the system pressure drop is not in the loop. It's in the horizontal piping and the reverse return manifold. So this tells me we can do better on this particular design. A total system pressure drop of nearly 160 feet ahead is the result of all these calculations. And I'll come back to that number shortly. We can also look at the shortest group, or 100 feet one way, and we notice that it would be much better than the furthest group in terms of its pressure drop, and starts to get closer to that desirable 70% number. So let's sort of state the problem. Due to the different lengths of the supply and return 2-inch pipes, the groups simply will not receive the design flow. And by the laws of fluid dynamics, the flow will simply redistribute in a manner that every group will have an identical pressure drop. We have a supply manifold, we have a return manifold. And every group is going to be exposed to those entering pressures and leaving pressures. So by definition, the pressure drops across all the groups will be identical. The flow is what changes to arrive at that equal pressure drop. So the 400-foot circuit will balance out by virtue of all this flow dynamics at 46.2 GPM or 15% below design. The 100-foot circuit is going to be 15% above design. So the problem, or is it? Assuming that each group has equivalent thermal performance, and that too could be a questionable assumption, but we got to start somewhere. To illustrate why it might be questionable, I did a job right here in Auburn, New York. We had 48 bores. 12 of them were exposed to an underground river. So I guarantee you those 12 loops are performing a whole lot better than the other 36. But aside from that, we'll start our assumption and analysis, assuming that each group is going to be somewhat equivalent in thermal performance. So to illustrate this, on a hot summer day toward the end of August or September, when our loop field is at maximum temperature, we've accumulated our cooling load through the season of cooling, and we're going to be sending potentially water out to the loop field at 100 degrees. Every group is going to get exposed to that same water temperature to dissipate heat into the ground. Therefore, with the same BTUs being transferred in each group, you can calculate what the return water temperature might be. Our 400-foot group operating at 46.2 GPM will be coming back at 88.2 degrees. The closest group might be coming back at 91.3 degrees. So a small difference in the delta T that's occurring due to the different flow rates in these groups. But the return water all comes back to the return manifold where all 23 circuits are going to mix together and average out to be 90 degrees. That is then sent to the heat pump to pick up that heat of rejection from the air conditioning load. And that's exactly what a perfectly balanced loop field would do. If every circuit were identical and we had a perfect 10-degree drop in temperature on every circuit, they would still average out to be returning to the heat pumps at 90 degrees. However, this flow balance is not the big problem. There's a much bigger problem. And that gets back to that 158.95 feet ahead pressure drop in this loop field. And based on my experience, I consider that an outrageous number. And let me illustrate why. Energy impact. If you look at each group at 54.4 GPM at 159 feet ahead, and assuming 80% pumping efficiency, it requires 2.73 horsepower on each group. 23 groups were up to 63 horsepower of pumping, and the engineer only specified a 50 horsepower pump. So right off the bat, we're not going to get the flow that we would like to have. And we can look at assuming an annual duty cycle of 30%. In other words, this pump is variable speed, is operating at different speeds throughout the year. We just pick 30%. We do the number crunching. it's going to cost over $18,000 a year just to operate the circulating system in this loop field. The pump energy is simply overcoming fluid friction, the flow through the pipes. Pumping energy turns into heat. Essentially, these pumps are going to contribute over 420 million BTUs into the loop field. That's the equivalent of adding 20 tons of extra cooling load to this system. So the impact of adding all that pump energy to the loop field is an upward shift in loop temperatures. I would say roughly 3 to 5 degrees hotter, just due to this frictional heat. And the efficiency of all the air conditioning units operating will be impacted by roughly 5 to 8%, which adds more heat to the loop field. So it's what we call the snowballing effect of making the system less efficient, which adds more heat, which raises temperature, which further reduces efficiency. So the bottom line is excessive pumping energy is a compounding threat. One, it's higher first cost for the pump itself. It's higher operating costs for the pump. It's increasing your air conditioning costs and an overall greater environmental impact, counter to the promise of geothermal. So let's go back to our little calculating sheet here. Excuse me. And look at maybe what we can do. First, look at the 2-inch pipe going out to these groups. That generates roughly a 94 feet of head pressure drop. Well, let's just bump that to 3-inch. Boom, we're down to 15 feet ahead. Very simple change. Improve the situation tremendously. Let's look at our reverse return header at 12.3 feet ahead. Seems high. So we're going to change what was called out in terms of reverse return header piping and increase that size. We've dropped that pressure drop now down to about 4 feet ahead. So all of a sudden, our 1.25-inch loop is 74% of the total system pressure drop. It will almost automatically, naturally balance at that point. However, we're not done. I think 52.8 feet ahead on the loop is too high of a pressure drop. We can do better. So we're going to go down to our table. We're going to pick an 1.5-inch loop. We drop the pressure drop, but now the loop is no longer above that 70% benchmark we're shooting for. So we go back and we look at that 3-inch pipe and say, let's make that 4-inch. And now we're getting our loop pressure drop to still be the dominant pressure drop of the system. Our total pressure drop is down around 35 feet. Things are looking pretty good right now. So this is for the furthest group. Let's take a look at the closest group at 100 feet. Pretty close, 32 feet ahead instead of 35 feet. Well, maybe I don't need 4-inch for that close group. So we'll drop that to 3-inch. And we start dialing in these groups so that we've created a very similar pressure drop and flow at close to our design flow objective. So let's look at the energy impact of making these changes. Horsepower's gone down from 60 down to 13. We look at our operating costs and energy, our pumping energy. We went from 420 down to 92 million BTUs. It's the equivalent of only adding 4 tons of extra cooling load. And the cooling efficiency is not impacted as greatly. So here's a little summary of that before and after design change. We've dropped pumping horsepower and the overall pumping impact by 78% by just changing some pipe sizes. So what more is there? Well, I look at 3.5 GPM per ton, and I remember the words of Dr. Kavanaugh that say you don't need to flow that high in a loop field. The heat pumps are perfectly happy anywhere from 2.25 to 3 GPM per ton. So let's go with 2.5. It drops our total system flow rate from 1250 GPM down to 892. And the total system pressure drop is now quite low. Let's look at this energy impact. We'll go through these same calculations and come up with another summary table. So now at 892 GPM, we've gone from 62 horsepower pump down to less than 6 horsepower. Our operating costs and overall energy impact of pumping has been reduced by 91%. There's more, because now we've reduced the load on the loop field by some equivalent 18 ton of air conditioning load. That's worth at least 4 loops. So if the original loop design had already factored in the pumping energy, and we've reduced pumping energy by 91%, we could probably reduce the size of that loop field by 4 loops. 2,000 feet of drilling at roughly $35 a foot, we're looking at $70,000 savings in the loop field. And I think that will more than make up for the extra cost of going to 3 to 4 inch pipe and from 1.25 to 1.5 loops. So going back to our calculator, this looks at our final design now with 88 loops, 890 some GPM, 21 feet ahead. This is what I'd call a good design. I want to move on to case study number 2. And this is one our friend Terry Proffer shared with me. He illustrated it in one of the previous Dig Deepers. And if ever I saw a loop field that was egregiously out of balance, let alone the other problems Terry talked about on this job. But you've got one group with 40 bores. You've got another 6 group with 20 bores. You've got one group with 18, one at 13, one at 9. You talk about a potential balance nightmare. This job is it. Now I went through and I looked at each of the 10 groups. I'm going to quickly go through these, and you can see how our calculator illustrates the performance of each of these groups. And I'll just go through them all quickly and arrive at a summary table. So here's our 10 groups, ranging from 9 bores per group to over 40 bores per group. I just don't understand why anybody would want to go that far out of balance. Now, we quite often have different sized groups, but we try to keep them somewhat close to each other. But even under this extreme case, the actual flow balance that will occur is roughly plus or minus 20%, with a couple of outliers. The 9 loop group will exceed design by roughly 40%, but all the other ones are still within plus or minus 20%. So it illustrates to me that, maybe we get too focused on trying to have a perfect balance, and we should be focused on designing the loop to perform well. So the energy impact of this particular job, I'll go through these numbers relatively quickly. I did come up with 102 horsepower pump, and Terry did share with me the original design did have 100 horsepower pump on it. It translates to roughly $35,000 a year operating cost just for the pumps. 800 million BTUs, or the equivalent of adding 38 ton of extra cooling load into that loop field. Again, same impact of having loop temperatures higher than what you'd like to see them. So again, I repeat this, that excessive pumping energy compounds in multiple ways. It's like double jeopardy squared. But frankly, adding a balance valve to this loop field would not solve the fundamental problems of this loop field. So in summary, my suggestion is do not use balance valves on loop field manifolds. Just a waste of money and adds pumping energy. You want to optimize the loop field and balance it through pipe sizing. And above all, be mindful of the compounding impact of pumping energy. It's huge. I did an energy audit of a geothermal system in Pennsylvania where the engineer, one, oversized the pump and felt it was good to operate it at full speed 24 hours a day, 7 days a week. It ended up the pumping energy was greater than all the heat pump energy combined. And that, to me, is almost sinful. So with that, I conclude my remarks and hopefully leave some time for some questions, answers, and I'll turn it back over to you, Jeff.
Thanks, John. Great presentation. I'm sure we'll have a lot of discussion here. I guess while we're waiting for questions to come into chat and Q&A, I have a couple myself, if that's okay.
No, I'm sorry, Jeff. You can't ask any questions.
That wasn't in the contract. Sorry. Yeah. So your first example, you went, according to the ASHRAE Blue Book, Kavanaugh Rafferty book, you went from a grade F pump selection to a grade A and grade A plus, really. Do you find that using that ASHRAE book for a guideline accomplishes the goals that you're using when you design? It seems to fit nicely.
Yeah, I certainly subscribe to the, what Dr. Kavanaugh and Kevin have pointed out in their articles and books and so forth. Because I think we all subscribe to the notion that geothermal is not being bought to brag about having geothermal. It's
Right.
being bought because of the promise of performance. And if we lose sight of the elements that make up the performance, we're missing the target on what geothermal can do.
Great comments. While we're waiting for some other questions here, I've got another one on your Reynolds number. You had 23% propylene glycol in that first example, and as we changed the pressure drop, how did you calculate how it affected the Reynolds number in each of those circuits? I didn't see that, but I was just curious because we really decreased the pressure drop significantly.
Yeah, well, the velocity through the loops all remained the same.
Okay.
And certainly the going from 1.25 loop to 1.5 loop, it's going to be a different Reynolds number. But in my calculating tool, when I drop below 2,500, it changes the formatting and gives me a red background. So it just sort of keeps me aware and mindful of that Reynolds number line in the sand that we try not to go below. And I think it's somewhat arbitrary. The transition from laminar to turbulent actually occurs anywhere from 2,000 to 4,000 Reynolds number. And the worst case scenario is long, smooth pipe. Well, that's what we got. So I'm not sure 2,500 is the hard line in the sand. I'd like to shoot for more like 3,500 to 4,000 to assure us that we have turbulent flow in those loops.
Very good point. And I'm glad to see 23% instead of 30% propylene glycol for sure. While we were discussing those points, Scott sent a question in the Q&A. He asks, how did you arrive at the 70% minimum loop head loss proportion, and why does that threshold mean it's self-balancing?
Well, certainly it took a long time for us to arrive at that. It sort of reflects what I call the extreme modeling. You can almost do a thought experiment that if you had very small lines going out feeding a bunch of circuits in parallel, and those circuits were much bigger in diameter, well, all the flow will go through the first loop. It'll never make it to the furthest loop. Um, and then you sort of work backwards, and you that 70% number is arrived at through experience and doing some pressure drop modeling and calculations. And since, pressure drop and the relationship to flow rate is a squared function, so really if you take the square root of 70%, which we'll call it about 90%, or 88, something like that, that sort of reflects the balance that you would get under that scenario. And I guess I can't really go back through how I arrived at it, but in detail right now, but we went through several iterations of trying to say, okay, if we're shooting for a plus or minus 5% balance, ideally, and I think we could live with plus or minus 10% flow imbalance and not see any thermal impact on the loop field, that this 70% factor that we've arrived at sort of is an indicator that we're in the right ballpark. That's all it really is.
That's great. Yeah, if you're like me, you live in spreadsheets, so you play a lot of what if scenarios over the years to figure that stuff out.
Yep.
Yeah, we're still waiting on some more questions, but I guess in the meantime, maybe you could talk a little bit about pumping and some of the experience you have. It fascinates me the difference between your first design and the second one. Have you found that engineers that you're working with are receptive to looking at these changes?
I've had the privilege of working with literally hundreds of engineers over the years. And I don't know what it is about engineers. I kid people. I say I got my PE license so that I could legally pick on engineers. So I've been authorized by the state of New York to pick on engineers. But they I have contractors who are more receptive to learning. And then I find engineers. It's just, they become fixated on thinking they got the answer and they don't want to open the can of worms and discover something different. Um, it's an interesting phenomenon, and I want to point out a couple engineers I've worked with over the years. One at Bureau Happold, his name was Alan Shepard. He's not the astronaut, but I worked on a job with him at Bard College, and the first time I met him at a design meeting, we went through the whole meeting, and afterwards he came up to me just thirsty for knowledge. He pulled me aside and we sat for 2 hours just talking about stuff. And I find that very refreshing. And I want to encourage engineers to embrace those opportunities to learn from folks in our industry who have literally decades of experience with dealing with this stuff. And I know there's literally hundreds of us out there. We're not that rare. So I want to encourage all engineers to just take the blinders off and really learn this stuff. It's full of a lot of nuance. It's not something you can just pick out of a textbook and run with it. You got to understand the implications of the choices you make.
I think that's the value in showing start to finish on that example you have. That's super helpful. Barry and Chad have some comments here in the chat. Barry says, great presentation. And then when the pump fails, the pump gets blamed. That's an interesting comment. Chad says, excellent presentation, John. Pumping efficiency needs to be addressed more as you have here, which I 100% agree. Barry comments, watts are dollars. So any reply to those comments?
Well, certainly, I think of hammered home the point that indeed pumping energy is like I said, it's a compounding threat. It's just dollars up front. It's dollars in operating costs. Its impact to the overall system efficiency. And I ballpark that first case study I used here, that if he had made the changes that I suggested over a 25-year period, that has $1 million value to the system. And yeah, some people may say, well, I don't want to go to a 3-inch pipe because it costs more. Well, I'm sorry. that's the reality. Deal with it. So it's just understanding these intricacies and dependencies on different aspects of a design. And yeah, to me, certainly selecting heat pumps and understanding the building load, those are all critically important. But I think often the loop field impact is just overlooked or not understood well enough. And that's sort of my focus over the years is, and a lot of the work we do, we simply do the loop field design and work with other mechanical engineers that are very good at doing the indoor side. So, but they're just unsure of the loop field side, and that's essentially how, we've carved out a slice of the business by offering that kind of service. And I think it's a good relationship because they can focus on what they do best and we can help them deal with the loop field side. That it does take a few decades to get the appropriate scar tissue to design these things.
Absolutely. Greg has a question comment here about watts affecting the cooling load, but also affecting the ground loop sizing and overall job cost. Do you find that those pump watts, which turn into heat of rejection, are calculated as part of the loop field sizing, or is that something that tends to be overlooked?
I think it's totally overlooked. As much as I applaud the software tools that we have available to us, I just don't think they capture that pumping impact in the loop sizing calculations as well as they should. They may to some degree, but I haven't found them. I have found my own spreadsheet tools to be a lot more useful in understanding the impact of pumping than using some of the loop field sizing software that's out there.
You almost have to place a virtual 4-ton heat pump or something like that in the software to make that work.
Exactly. We end up doing that quite often on, loads like domestic hot water load. I don't like the modeling that's done within the loop field software itself. So we impose a 8760 domestic hot water model and dovetail it into our input into the loop sizing model to feel more comfortable that we're truly modeling what we think we're going to end up with.
Great way to do that. Jared has a question about the manifold valve. Does the valve need to be the same size as the pipe?
Good question. In the first case study where we have some circuits going out at 4-inch and maybe the closest ones are going out at 3-inch, I would reduce them all down to 3-inch before coming into the building and connecting to the manifold, and then make each circuit have a 3-inch butterfly valve on the inside, because the real impact of these lengths of supply and return is all about the length of the pipe. It's not about the diameter. So reducing it down from 4-inch to 3-inch and then coming into the manifold has a minimal impact. And it just makes, from a practical standpoint, a whole lot more sense to come through the wall with all the same size holes and pipes and metro seals, all the hardware, and have consistent sizing in all the branch circuit valves I just think it makes for a cleaner package without getting hung up on the slight impact of reducing back down to from 4 inch to 3 inch.
Excellent. Plus save some costs there too.
Yep.
Mike made a comment here. We need to hear more often from John and others that subscribe to this mentality. He's defining true/real honest engineering, not copy and paste. Any comments on that?
Thank you. I appreciate the comment.
And Tom echoes that sentiment. Great presentation, John. Dr. Kavanaugh's ash rate publication provides detailed calculations of the impact of ground leak flow imbalance as well in Appendix G. That's a really good point.
Good.
Scott has a question. Is there a threshold you've seen when balancing valves are required for interior pipe runs to heat pumps?
Yeah, certainly the value of a balance valve is when you get into the actual hardware that, like multiple heat pumps in a system, it's so hard to predict exactly which ones are going to gobble up more flow than they should and so forth. So when you get above a certain number of heat pumps, it's just not practical to do anything other than put a balance valve on every heat pump and leave it up to the system balancer to dial in every heat pump as it should be. When you get into the smaller, maybe 4 to 10 heat pumps, and you can identify the bad characters, if you will, the ones that already had the highest pressure drop, then I wouldn't restrict their flow anymore. I would simply put a balance valves on the remaining heat pumps that otherwise would gobble up extra flow and deprive that one high pressure drop heat pump from getting adequate flow. So you balance the flow on some of the heat pumps, but not necessarily all of them. But from a practical standpoint, you reach a point where you've got the piping dynamics are so hard to truly analyze. I mean, we've done some pretty complex jobs, but you reach a point where you just put a balance valve on every heat pump and dial it in. Yeah, you're going to pay a pumping penalty because you're restricting the flow on every heat pump, which is worth avoiding if you can, but sometimes it's just not practical.
Very good. Well, we are right on time. We've got about 4 minutes to spare. Thank you so much, John, for the presentation. Thank you for attendees and the great questions. We need more of these types of discussion in our industry, and I think we'll have even more success. So thanks so much, everyone. Have a great weekend. Appreciate your time, John. And the recording will be online and probably beginning of the week.